On the night of December 27th, 2024, in the dry, clear air above the Chilean Andes, a robotic telescope did something it had done every clear night for years. It opened its shutter, collected photons, and compared what it saw against what should have been there. On most nights, everything matched. The stars sat where they belonged. The planets moved at their predicted rates. The sky was orderly, familiar, unremarkable. But on this particular night, 4 faint smudges of light appeared in positions where nothing should have existed. 4 tiny points, barely distinguishable from the electronic noise of the camera's detector, drifting slowly against the ancient backdrop of fixed stars. The telescope belonged to a network called ATLAS, the Asteroid Terrestrial Impact Last Alert System, a collection of instruments scattered across the globe whose sole purpose is to catch rocky visitors from the depths of space. ATLAS scans the entire visible sky roughly once every 24 hours, cataloguing everything that moves. On a typical night, the software identifies dozens of objects, fragments of asteroids tumbling through near-Earth space, most of them already known, most of them on orbits that pose no threat whatsoever. They are recorded, cross-referenced against the existing catalogue, and forgotten within hours. The machinery of asteroid detection is, by design, mundane. It is meant to be. Because the alternative, the scenario in which the machinery discovers something genuinely alarming, is a scenario nobody wants to face. On December 27th, the machinery discovered something genuinely alarming, and it would take weeks for the full weight of that discovery to become clear. The object was given a designation, a string of characters assigned by the Minor Planet Center, 2024 YR4. It was estimated, based on its brightness and distance, to be roughly 50 to 60 meters across, about the height of a 10-story building, about the length of an Olympic swimming pool and a half, about the same size as the Leaning Tower of Pisa. If you could somehow pry it from the ground and hurl it through space at tens of thousands of kilometers per hour, in the catalogue of known near-Earth objects, which by late 2024 numbered more than 37,000, 2024 YR4 was unremarkable in size. It was not a planet killer. It was not the kind of monster that carved the Chicxulub crater and ended the reign of the dinosaurs. It was small. But small, in the language of planetary defense, does not mean harmless. A 50 to 60 meter rock striking Earth at typical asteroid velocities would release energy equivalent to approximately 8 million tons of TNT. To make that number meaningful, compare it to the most destructive single weapon ever used in warfare. The atomic bomb dropped on Hiroshima on August 6, 1945, which released energy equivalent to roughly 15,000 tons of TNT. 2024 YR4, upon impact, would release 500 times that amount, 500 Hiroshimas, concentrated in a single point, in a single instant. Within days of its discovery, automated impact monitoring systems at NASA's Jet Propulsion Laboratory in Pasadena, California, and at the European Space Agency's Operations Center in Frascati, Italy, calculated that this object had a non-zero probability of striking Earth. Not in the distant future, not in some abstract time frame measured in centuries, but on a specific date, December 22nd, 2032, less than 8 years away. The initial probability was approximately 1%, 1 in 83. In the world of asteroid tracking, where typical impact probabilities for newly discovered objects are measured in millionths of a percent, 1% was extraordinary. It was the kind of number that made seasoned planetary scientists pause, double-check their calculations, and then pause again. And then the number went up. Over the following weeks, as telescopes around the world aimed at this faint, retreating speck of light, the impact probability climbed. 1.3%, 2.1%, 2.6%. And finally, on February 18, 2025, it reached 3.1%, 1 in 32. 2024 YR4 became the highest-risk asteroid in the recorded history of NASA's impact monitoring systems, higher than Apophis, the 375-meter behemoth that had briefly terrorized the world in 2004, higher than any other rock ever tracked. And the risk corridor, the strip of Earth's surface where the asteroid might impact, stretched across some of the most densely populated regions on the planet. From the eastern Pacific across South America, through sub-Saharan Africa, over the Arabian Sea, and into South Asia. More than 100 million people lived within that narrow band of potential annihilation. Cities like Bogota, Lagos, Mumbai, and Dhaka lay beneath the possible path. The Chelyabinsk meteor of February 2013 had been roughly 20 meters across, one-third the diameter of this rock. It injured over 1,500 people and shattered windows across 6 cities without ever touching the ground. 2024 YR4 was 3 times larger. If it struck, the question would not be how many windows broke, it would be how many city blocks ceased to exist. But the most unsettling part of this story is not the probability, it is the pattern. For nearly every asteroid ever discovered, the trajectory of risk follows a predictable and comforting arc. Discovery, brief alarm, more observations, probability drops to 0, threat removed. It happens dozens of times a year, so routinely that almost nobody notices. With 2024 YR4, that arc inverted. More data brought more danger. Every new observation pushed the probability higher rather than lower. The familiar script of reassurance did not apply, and for the first time in the history of modern planetary defense, the world found itself in a scenario it had practiced in tabletop exercises, but never experienced for real. A genuine, escalating, credible threat of asteroid impact within a single human lifetime. By the end of tonight, you are going to understand exactly what happened, how this rock was found, why the numbers refused to cooperate, how the most powerful telescope ever built was drafted into service as a planetary defense instrument, what the response revealed about our readiness and our vulnerability, and why, even though the immediate danger has passed, the story of 2024 YR4 may be the most important warning the universe has ever sent us. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand the full gravity of what happened with 2024 YR4, we first have to understand the place where it happened. Not the Chilean telescope, not the NASA control room, the place itself, the solar system, the actual physical environment in which Earth exists, and in which rocks like 2024 YR4 are right now silently hurtling through the darkness. Most people carry a mental image of the solar system that is frankly a lie. The tidy textbook diagram, planets spaced evenly along concentric circles, vast empty gulfs between them, the whole arrangement serene and orderly. That image is useful for teaching children the names of the planets. It is dangerously misleading for understanding the reality of living in space. The real solar system, the one you inhabit at this very moment, is a debris field, a cosmic construction site that was never cleaned up. 4.6 billion years ago, when the sun ignited and began fusing hydrogen in its core, the disk of gas and dust that surrounded it began to coalesce into larger and larger bodies. Most of that material was swept up by the 8 planets and their moons. But a staggering amount was left behind. Rocky fragments, metallic shards, icy remnants, all of it in constant, slow, chaotic motion, drifting on orbits shaped by the gravitational tides of Jupiter, Saturn, and the other giant planets. The most well-known reservoir of this debris is the asteroid belt, a broad ring of rocky objects orbiting the Sun between Mars and Jupiter, roughly 2 to 3.3 astronomical units from the Sun. An astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. The belt contains millions of objects, ranging from dust-sized particles to Ceres, a dwarf planet 946 kilometers in diameter, large enough to be spherical under its own gravity. If you gathered every object in the asteroid belt and combined them into a single body, the result would have only about 4% the mass of the Moon. Spread across the vast volume of the belt, the average distance between individual asteroids is millions of kilometers. Spacecraft have flown through the belt repeatedly without incident. It is not the dense, perilous obstacle field depicted in science fiction films, where ships dodge tumbling boulders at every turn. It is, for the most part, extraordinarily empty, but the belt is not sealed, it leaks. Gravitational interactions with Jupiter, whose immense mass dominates the dynamics of the inner solar system, continually perturb the orbits of belt objects. Certain orbital resonances with Jupiter create unstable zones within the belt, regions where an asteroid's orbit is repeatedly nudged in the same direction until, over millions of years, the asteroid is flung onto a new path that crosses the orbits of the inner planets. Other mechanisms contribute as well. Collisions between belt objects can send fragments careening onto new trajectories, and the gentle pressure of sunlight, absorbed and re-emitted as heat, can slowly alter an asteroid's orbit over geological timescales through a process called the Yarkovsky effect. The result of all these mechanisms is a population of objects that have escaped the belt and now travel through the inner solar system, crossing the orbits of Mars, Earth, Venus, and even Mercury. These are the near-Earth objects. As of the mid-2020s, more than 37,000 have been catalogued. But that number, impressive as it sounds, is a tiny fraction of the total. Estimates suggest that the number of near-Earth objects larger than 10 meters in diameter is in the tens of millions. Objects larger than 140 meters, the size threshold at which an impact could devastate an entire region, number roughly 25,000, of which fewer than 40% have been found. And objects in the 50 to 100 meter range, the Tunguska class impactors, the city killers, those are estimated to number in the hundreds of thousands or possibly millions. The vast majority remain undiscovered. They are out there, right now, moving on orbits that are unknown to anyone, invisible to every telescope on Earth, until the moment they are either found or arrive. The history of Earth bears the scars of these invisible visitors. Every continent, every ocean floor, every ancient shield of rock exposed by erosion records the evidence of bombardment. The most dramatic example is the Chicxulub impact, the event that ended the Mesozoic era and wiped out the non-avian dinosaurs 66 million years ago. The impactor, an asteroid or comet roughly 10 to 15 kilometers in diameter, struck what is now the northern coast of the Yucatan Peninsula in Mexico at a velocity of roughly 20 kilometers per second. The collision released energy estimated at 100 trillion tons of TNT, more than 10 billion times the combined yield of every nuclear weapon ever built by humanity. The impact excavated a crater 180 kilometers in diameter. It vaporized billions of tons of rock, launching superheated debris into suborbital trajectories that rained back down across the entire planet, igniting global firestorms. Trillions of tons of sulfur and dust were injected into the upper atmosphere, blocking sunlight for months or years and triggering a global winter that collapsed food chains worldwide. 75% of all species on Earth went extinct. If you wanted to visualize the scale of the Chicxulub impactor relative to the solar system, consider this. If you shrank the sun to the size of a basketball and placed it in the center of a football field, the Earth would be a small pea about 26 meters away. Jupiter would be a golf ball at 134 meters. And the Chicxulub asteroid, the object that ended the age of the dinosaurs, would be a particle too small to see with the naked eye. A grain of dust, that is the scale of the threat. Something so small you could not find it on the field, traveling so fast you could not see it move, carrying enough energy to reshape the entire biosphere of a planet. Chicxulub-class impacts are extraordinarily rare, occurring on timescales of tens to hundreds of millions of years. At any given time, the probability of such an event occurring within a human lifetime is vanishingly small. But smaller impacts by objects in the tens to hundreds of meters range, are far more common. They occur on timescales of centuries to millennia, and their potential for damage, while not global, is more than sufficient to destroy cities, trigger tsunamis, and cause casualties in the millions. The most dramatic example in recorded history is the Tunguska event. On the morning of June 30th, 1908, something entered Earth's atmosphere above the remote wilderness of central Siberia, near the Podkamennaya Tunguska River. The region was home to a scattering of Evenki reindeer herders, semi-nomadic people who lived in the vast taiga forest that stretches across northern Russia like a green ocean. At approximately 7:15 in the morning local time, eyewitnesses reported seeing a column of bluish-white light moving across the sky as bright as the sun. Then came a flash of searing intensity, followed by a sound like cannon fire and then a shock wave that flattened everything in its path. The object, now believed to have been a stony asteroid roughly 50 to 100 meters in diameter, in the same size class as 2024 YR4, never reached the ground. It exploded in the air at an altitude of 5 to 10 kilometers, an event known as an airburst. The energy released was estimated at 10 to 20 megatons of TNT. For scale, the most powerful nuclear weapon ever detonated by the United States. The Castle Bravo test of March 1, 1954, yielded 15 megatons. The Tunguska airburst was in the same range as a thermonuclear bomb. The blast flattened an estimated 80 million trees over an area of roughly 2,100 square kilometers, an area larger than the City of London. Trees were snapped like matchsticks, all radiating outward from a central point. The shockwave was detected by barometric stations across Europe. Seismic instruments registered the event. For several nights following the explosion, the skies across Europe and Western Asia glowed with a strange luminescence, bright enough to read a newspaper by at midnight, believed to have been caused by fine particles lofted into the upper atmosphere and illuminated by the setting sun. Because of the extreme remoteness of the site, the first scientific expedition did not reach Tunguska until 1927, nearly 2 decades later. Led by the Russian mineralogist Leonid Kulik, the expedition found a landscape of devastation. Thousands of square kilometers of forest had been flattened, with tree trunks lying parallel to the ground, all pointing away from the epicenter. But there was no crater, no fragments, no remnants of the impactor. It had been entirely consumed in the explosion, vaporized by the tremendous heat generated by its passage through the atmosphere. The crucial fact about Tunguska is the one that haunts planetary defense scientists to this day. The Earth rotates on its axis at roughly 1,600 kilometers per hour at the equator. If the Tunguska object had arrived 4 hours and 52 minutes later, the rotation of the Earth would have placed the impact point directly over St. Petersburg, then the capital of the Russian Empire, a city of more than 2 million people. The entire city, with its imperial palaces, its cathedrals, its universities, its population, would have been obliterated, and no one would have had any warning, because in 1908 there was no system to detect incoming asteroids. The sky was a black curtain from which objects emerged unannounced. That was the state of affairs for most of human history. For all the achievements of astronomy, from the ancient Babylonians, who charted the planets, to the modern telescopes that photograph galaxies billions of light years away, the detection of small, fast-moving objects that could strike Earth remained beyond the reach of science until remarkably recently. The field of planetary defense, the systematic effort to find, track, and potentially deflect threatening asteroids, is barely 3 decades old. The first serious push to address the impact hazard came in the wake of 2 events that transformed the issue from a theoretical concern into a visceral, undeniable reality. The first was the growing body of evidence, culminating in the 1980s and 90s, that the Chicxulub impact had actually occurred and had been directly responsible for the mass extinction at the end of the Cretaceous period. The discovery of the crater itself, buried beneath the Yucatan Peninsula, confirmed that the dinosaurs had not simply faded away. They had been killed, suddenly and violently, by a rock from space. The second event was the collision of Comet Shoemaker-Levy 9 with Jupiter in July of 1994. The comet had been captured by Jupiter's gravity during a previous close approach and had been torn into more than 20 fragments by tidal forces. In July of 1994, those fragments plunged into Jupiter's atmosphere one by one, over the course of 6 days, in an event observed by virtually every major telescope on Earth and by the Galileo spacecraft, then en route to Jupiter. Each fragment produced a fireball thousands of kilometers across, a plume of superheated gas rising thousands of kilometers above the cloud tops, and a dark scar in Jupiter's atmosphere that was visible for months. The energy released by the largest fragments was estimated at 600 times the combined yield of every nuclear weapon in the world's arsenals. It was the first time human beings had witnessed a cosmic impact in real time, and the images were seared into the scientific consciousness. The message was unmistakable. This can happen. This does happen. And if it can happen to Jupiter, it can happen here. In 1998, the United States Congress directed NASA to find and catalogue at least 90% of all near-Earth objects larger than 1 kilometer in diameter within 10 years. This mandate, known as the SpaceGuard Survey, was driven by a clear-eyed calculation. Objects larger than 1 kilometer, upon impact with Earth, could trigger global consequences comparable to the Chicxulub event, mass extinction, the collapse of agriculture, the end of civilization as we know it. Finding and tracking every such object was, by any reasonable assessment, a priority for the survival of the species. The SpaceGuard survey was largely successful. By its target date of 2008, the vast majority of near-Earth objects in the kilometer and larger size class had been identified and found to be on orbits that posed no threat within the foreseeable future. That was the good news. The bad news was that the survey left a gaping hole. Objects smaller than 1 kilometer were far more numerous and far harder to find. In 2005, Congress updated the mandate, directing NASA to find 90% of near-Earth objects larger than 140 meters by 2020. That deadline was not met, and as of the mid-2020s, the search continues. The challenge is immense. Small asteroids are faint. They are often visible only when they are already close to Earth, and the sky is vast. The instruments built to meet this challenge represent quiet marvels of engineering and dedication. Atlas, the system that discovered 2024 YR4, was designed specifically to detect small near-Earth objects on final approach. Its telescopes, equipped with wide-field cameras, sweep the entire visible sky every night, searching for anything that moves. Atlas is not designed to find asteroids years in advance. It is designed to sound the alarm when an object is days or weeks from impact, providing enough warning for civil defense, for evacuation, even if not enough time for deflection. It is, in the most literal sense, a last line of defense. The Catalina Sky Survey, operated by the University of Arizona, has been finding near-Earth objects since the early 2000s and remains one of the most prolific discovery programs in the world. PanSTARRS, the Panoramic Survey Telescope and Rapid Response System, uses some of the largest digital cameras in existence to scan the Hawaiian sky for faint movers. Together with space-based assets and a growing network of international observatories, these programs form the backbone of humanity's early warning system against cosmic impacts. The raw detections from these telescopes flow to the Minor Planet Center in Cambridge, Massachusetts, which serves as the global clearinghouse for observations of newly discovered objects. From there, the data moves to the Impact Monitoring Centers, NASA's Center for Near-Earth Object Studies, CNEOS, at the Jet Propulsion Laboratory, which maintains the Sentry Risk Assessment System, and the European Space Agency's Near-Earth Object Coordination Center, NEOCC, in Italy. These centers perform the critical calculation. Given all available observations, what is the probability that this object will hit Earth, and when? For most of the history of these systems, the risk tables have been populated by objects with vanishingly small impact probabilities, numbers so close to zero that they register as statistical noise. Objects appear on the CAD tables briefly, then vanish as new observations refine their orbits and exclude an Earth impact. This cycle of discovery, brief alarm, and rapid resolution is the normal mode of operation. It repeats dozens or hundreds of times per year, generating no public attention whatsoever. But a few objects have broken the pattern. Before 2025, the most significant was Apophis, asteroid 99942, discovered in June of 2004 by astronomers Roy Tucker, David Tholen, and Fabrizio Bernardi at Kitt Peak National Observatory in Arizona. Apophis was a formidable object, roughly 375 meters in diameter, about the length of an aircraft carrier. In late December of 2004, orbital calculations indicated that Apophis had a 2.7% chance of striking Earth on April 13, 2029. For 4 dramatic days, it held a rating of 4 on the Torino Impact Hazard Scale, the international 10-point system for communicating asteroid threats. Level 4 is described as a close encounter with a significant chance of localized destruction. No object had ever reached that level before. the astronomical community was, for those 4 days, deeply and genuinely concerned. A 375-meter asteroid striking Earth would release energy equivalent to roughly 1,200 megatons of TNT, enough to devastate an area the size of a small country. Fortunately, additional observations over the following weeks refined the orbit of Apophis and steadily reduced the impact probability to 0. The asteroid was ultimately removed from the Century Risk Table entirely in 2021, after radar observations confirmed that it would pass safely by Earth in 2029 at a distance of roughly 32,000 kilometers, closer than geostationary satellites, but still a clean miss. Apophis will, in fact, be visible to the naked eye during its 2029 flyby, a slow-moving star-like point drifting across the sky, visible to more than 2 billion people across Africa and Western Europe. It will be one of the great astronomical spectacles of the 21st century, a moment when humanity will watch a 375-meter rock glide past at a distance less than 1/10 that of the Moon. But the Apophis episode left a permanent mark on the field of planetary defense. It proved that the detection and risk assessment systems worked. It demonstrated that the global astronomical community could coordinate a rapid response, and it set a benchmark, a high-water mark for asteroid risk that stood unchallenged for 2 decades, until December of 2024, until a faint point of light appeared in the Chilean data, and the numbers began to climb in a direction nobody expected. The discovery of 2024 YR4 began, like so many pivotal moments in science, with a machine doing exactly what it was designed to do. On the night of December 27, 2024, the Atlas telescope at its station in Rio Hurtado, Chile, observatory code W68 in the Minor Planet Center's catalogue, captured a sequence of images as it swept the sky. Embedded in those images, the detection software identified a faint moving point of light, an object drifting slowly against the stationary background of stars. The detection was entirely automated. No human sat at the telescope squinting through an eyepiece. No astronomer leaned back in a chair and muttered, "That is strange." The discovery was made by algorithms, by mathematical routines designed to separate the objects that move from the billions that do not. This is how the vast majority of asteroids are found in the modern era, not by the drama of human observation, but by the relentless, tireless, unseeing patience of software. The object was extraordinarily faint. Its apparent magnitude placed it near the detection threshold of the Atlas system, meaning it was barely brighter than the background noise of the sky. This faintness could mean several things. The object was very small, very far away, or very dark, some combination of all three. At this point, nothing about the detection was remarkable. Atlas finds dozens of faint movers every month. Most turn out to be previously uncatalogued objects on benign orbits. The system processes them, reports them, and moves on. The preliminary orbit calculation, however, told a different story. To calculate the orbit of a newly discovered asteroid, you need at least 3 positions, measured at different times. From those positions, and the laws of celestial mechanics, you can reconstruct the path the object is following through space. The more observations you have, and the longer the time span they cover, the more precisely you can determine the orbit. With only a handful of observations spanning a few hours, the orbit is known only approximately. The uncertainty is large. The object could be on any one of a vast family of possible paths, each consistent with the few data points available. Within days of the initial detection, astronomers began the standard process of gathering additional data. David Rankin, an astronomer at the Catalina Sky Survey at the University of Arizona, searched the survey's archival images and found that 2024 YR4 had actually been captured before its official discovery in images taken on December 25th. This pre-discovery recovery extended the known arc of observations backward in time, providing a longer baseline for the orbital calculation. Additional data came from Pan-STARRS in Hawaii and from other Atlas stations around the world. The orbit began to take shape, and the shape it took was disturbing. The initial calculations performed independently by both CNEOs at NASA's Jet Propulsion Laboratory and the NEOCC at the European Space Agency converged on a sobering conclusion. The asteroid had a roughly 1 in 83 chance, approximately 1.2%, of striking Earth on December 22, 2032. The object was immediately placed at the top of both the Sentry Risk Table and the ESA's Neo-Impact Risk List. It was assigned a Torino Scale rating of 3, a level that had never been assigned to any asteroid before. The description for level 3 reads, "A close encounter, meriting attention by astronomers. Current calculations give a 1% or greater chance of collision capable of localized destruction." Now, a 1.2% impact probability might sound small. In the context of daily life, you would not rearrange your schedule over a 1% chance of rain. But asteroid impact probabilities do not operate on the same scale as weather forecasts. The baseline probability, the normal expected impact probability for a newly discovered near-Earth object, is typically on the order of 1 in a million or less, often far less. 1.2% is not slightly elevated. It is elevated by a factor of 10,000 or more above the norm. In the 25-year history of the Sentry system, only a handful of objects had ever exceeded 1%, and all of them had been rapidly reduced to zero as new observations came in. 2024 YR4 was different from the start, and the difference would only grow. Here is the fundamental problem, and it is one that lies at the heart of every asteroid scare, every near miss, and every moment of uncertainty in the history of planetary defense. When you first discover an asteroid, you see it in one small region of the sky at one moment in time. From those initial observations, you can compute a range of possible orbits. That range is wide. It represents all the paths through space that are consistent with what you have observed so far. Earth occupies a specific, finite volume of space along the asteroid's potential trajectory. The impact probability is simply the fraction of the range of possible orbits that leads to an intersection with Earth. Now, in the vast majority of cases, as you gather more observations and refine the orbit, the range of possibilities shrinks, and almost always, the refined range excludes Earth. The impact probability drops to zero, sometimes within hours. This is the normal pattern, and it is the reason that most asteroid scares are resolved quickly and quietly. The few data points you start with suggest a wide highway of possible paths. As you add more data, the highway narrows to a single lane, and that lane almost never runs through Earth. But occasionally, and this is the critical exception, the initial data are consistent with an orbit that brings the asteroid very close to Earth. In those cases, the range of possibilities already includes Earth, and as new observations narrow the range, the narrowing does not push the predicted path away from Earth. Instead, it concentrates the most likely trajectory closer to the impact zone. The probability goes up. Each new measurement, rather than providing reassurance, confirms that the asteroid's most probable path passes dangerously close to our planet. This is exactly what happened with 2024 YR4. The initial observations placed the asteroid on a family of orbits that included trajectories very near Earth. As additional data arrived in late January and February of 2025, the orbit was refined, but the refinement converged toward the danger zone rather than away from it. The impact probability did not drop, it climbed steadily, relentlessly. In late January, the probability rose from 1.2% to 1.3%, then jumped to 2.1%. This was already extraordinary. In the entire history of the Sentry system, only Apophis had briefly exceeded 2%, and that had lasted less than a week. 2024 YR4 had been above 1% for weeks, with no sign of declining. By the second week of February, the probability had climbed to 2.6%. NASA published the Impact Risk Corridor, a narrow band across the Earth's surface where the asteroid would strike if it turned out to be on a collision course. The corridor ran from the eastern Pacific Ocean, across Colombia, over the Atlantic, through West Africa including Abidjan in the Ivory Coast, and Lagos in Nigeria, then across Sudan including Khartoum, over the Arabian Sea, and into South Asia, crossing Mumbai, Kolkata, and Bangladesh. More than 100 million people lived within this strip. The potential energy of the impact was calculated at approximately 8 megatons of TNT, 500 times the Hiroshima bomb, devastating, unsurvivable at close range. The International Asteroid Warning Network, IORN, a United Nations-endorsed body that coordinates the global response to potential asteroid impacts, took a step it had never taken before for a real-world scenario at this level. IORN issued a potential asteroid impact notification, a formal communication to governments and space agencies worldwide that a credible elevated asteroid impact risk existed. This was not a drill. This was not an exercise. This was the system responding to a genuine threat assessment, using the protocols that had been designed precisely for this purpose. On February 18, 2025, the probability was revised once more, 3.1%, 1 in 32. 2024 YR4 had now eclipsed the all-time record set by Apophis. It was the highest threat asteroid in the entire history of modern asteroid tracking systems. And unlike Apophis, whose peak rating had lasted only 4 days, 2024 YR4 had been elevated for weeks, and the upward trend showed no sign of slowing. Let that sink in. The most dangerous asteroid ever recorded by NASA. A 1 in 32 chance of city-scale destruction. An impact corridor stretching over half the planet. And the numbers were still going up. And it gets worse. Because as the probability climbed, the asteroid was leaving. It had made its closest approach to Earth on December 25, 2024, 2 days before its discovery, passing at a distance of roughly 829,000 kilometers, about 2.15 times the distance to the Moon. By the time it was found, it was already receding, and every day that passed it moved farther away, growing fainter as the distance increased. Ground-based telescopes were racing the clock. The asteroid was fading. By mid-March of 2025, it would drop below the detection threshold of every ground-based telescope on Earth. After that, it would be invisible for roughly 3 years, until late 2028, when its orbit would bring it close enough to the Sun to be illuminated again and close enough to Earth to be detected. The implications of this timeline were stark. If the impact probability was not resolved before the asteroid vanished from view, the world would face 3 years of uncertainty. 3 years of not knowing whether a 500 Hiroshima equivalent rock was heading for a city. 3 years during which no additional data could be collected to refine the orbit, and 3 years lead time for a deflection mission, if one turned out to be necessary. When the asteroid reappeared in 2028, there would be only 4 years until the potential impact date. Whether 4 years would be sufficient to design, build, launch, and execute a deflection mission was, at best, uncertain. The DART mission, which successfully deflected the asteroid Dimorphos in 2022, had taken 7 years from initial concept to impact. 4 years might not be enough. The pressure to gather additional data was immense. Every available telescope was pointed at the receding asteroid. The Gemini South Telescope in Chile, one of the largest optical telescopes in the southern hemisphere, captured images of 2024 YR4 on February 7th, when it was roughly 59.5 million kilometers from Earth. The observations were challenging, taken under conditions of elevated sky brightness, but they yielded additional positional data that helped refine the orbit. And then came the decision that would change everything. A decision to aim the most powerful space telescope ever built at a small, fast-moving rock in our own cosmic neighborhood. The James Webb Space Telescope is not an asteroid hunting instrument. It was conceived in the 1990s, designed through the 2000s, constructed through the 2010s, and launched on December 25, 2021, precisely 3 years before 2024 YR4 made its closest approach to Earth. Its 6.5-meter primary mirror, composed of 18 gold-coated hexagonal segments of beryllium, gives it a light-collecting area more than 6 times that of the Hubble Space Telescope. It operates from a gravitationally stable point called the second Lagrange point, roughly 1.5 million kilometers from Earth, far beyond the Moon, where it orbits the Sun in lockstep with our planet. Its instruments are cooled to temperatures near absolute zero, 40 kelvins, negative 233 degrees Celsius, allowing it to detect the faintest infrared emissions from the most distant objects in the universe. Webb was designed to look at galaxies 13 billion light-years away, to study the atmospheres of exoplanets orbiting distant stars, to observe the birth of stars in vast, cold molecular clouds. Pointing it at a 60-meter rock a few tens of millions of kilometers from Earth was, by any measure, an unconventional use of the most expensive scientific instrument ever placed in space. But the situation demanded it. Andrew Rivkin of the Johns Hopkins University Applied Physics Laboratory, a planetary scientist who had played a leading role in the DART asteroid deflection mission, submitted a proposal for director's discretionary time on the WST. Director's discretionary time is a special reserve of observing hours, held back from the normal peer-reviewed allocation process, for use in situations of unusual scientific urgency. The proposal was reviewed and approved with exceptional speed. On February 18th and again, on February 26th of 2025, the James Webb Space Telescope turned away from the distant cosmos and focused its infrared gaze on 2024 YR4. The observations accomplished two things of immediate and profound importance. First, by observing the asteroid in infrared wavelengths, both near-infrared using the INIARCam instrument and mid-infrared using the MIRI instrument, Webb detected the thermal radiation emitted by the asteroid's surface. This thermal data provided a direct measurement of the asteroid's size, independent of assumptions about its reflectivity. Ground-based estimates had placed the diameter between 40 and 100 meters, a range so wide that it spanned the difference between a severe but survivable regional event and a catastrophic city-destroying impact. Webb narrowed the measurement to approximately 60 meters, plus or minus 7. 2024 YR4 was, in Rivkin's words, a building-sized object, roughly the height of a 15 to 20-story apartment tower. If you could somehow pluck it from space and set it down on a city block, it would reach the rooftop of a mid-rise building. This was the rock that had held the title of highest risk asteroid in recorded history. The JWST also obtained spectral data that helped determine the asteroid's composition. Analysis of the light reflected and emitted by the surface suggested that 2024 YR4 is most likely an S-type asteroid, a stony object composed primarily of silicate minerals and nickel iron. This placed it in the same broad compositional category as many main-belt asteroids, and notably, in the same class as the Tunguska impactor. The asteroid's rotation period was measured at approximately 19.5 minutes, meaning it completes a full turn on its axis roughly every 20 minutes. Fast-spinning, small, stony, and hurtling through the inner solar system on a 4-year orbit, a typical member of the vast, unseen population of near-Earth objects, unremarkable in every way except for the terrifying precision with which its orbit threaded the needle of Earth's position in space. The second critical contribution of the JWST observations was positional data. Webb's precise measurements of the asteroid's position at known times provided additional constraints on the orbit, data that no ground-based telescope could match as the object faded from view, and these new data contributed to a dramatic reversal in the trajectory of risk. On February 19, 2025, NASA announced that overnight observations, including data from multiple sources, had reduced the impact probability from 3.1% to 1.5%. The number had finally turned. The orbit was being refined, and for the first time, the refinement was pushing the predicted path away from Earth. The next day, the probability dropped further to 0.28%, a Torino Scale rating of 1. The description for level 1, a routine discovery in which a pass near the Earth is predicted that poses no unusual level of danger. Current calculations show the chance of collision is extremely unlikely with no cause for public attention or public concern. And on February 23, 2025, the probability of an Earth impact was reduced to effectively 0. The numbers, which had climbed for weeks, which had reached a historic peak that surpassed every previous asteroid threat, had finally collapsed. 2024 YR4 would not hit Earth. The announcement was blunt, bordering on celebratory. In the words of one widely shared communication from NASA, that is impact probability 0. The system had worked. From the automated detection by Atlas in Chile, to the precovery by the Catalina Sky Survey, to the multinational observation campaign involving telescopes across 3 continents, to the emergency deployment of the most powerful space telescope in existence. The planetary defense infrastructure had performed its function. The threat had been detected, assessed, escalated, monitored, and ultimately resolved. It was in many ways a triumph, but the triumph was incomplete, because when the Earth impact was excluded, the orbital calculations revealed something unexpected. The predicted trajectory for December 22, 2032, while clearly missing Earth, passed very close to the Moon. Subsequent analysis showed that the probability of a lunar impact initially stood at approximately 4.3%. The asteroid might hit the Moon. A lunar impact would pose no direct threat to human life. Nobody lives on the Moon. But the scientific and symbolic significance would be extraordinary. No asteroid impact on the Moon has ever been predicted in advance and then observed. Watching a known asteroid strike the lunar surface, with every telescope on Earth and in orbit pointed at the event, would provide direct data on impact mechanics, crater formation, and the properties of the lunar regolith that would be invaluable for planetary science and defense. It would also be a visceral, unforgettable reminder that cosmic impacts are not ancient history. They are ongoing events in our own neighborhood, happening in real time. But here is what makes this truly terrifying. The lunar impact probability could not be resolved from the ground. By March of 2025, the asteroid had faded below the detection threshold of all ground-based telescopes. It would not become visible again until late 2028. The 4.3% chance of a moon strike, a probability nearly as high as the peak Earth impact odds, would hang unresolved for months, possibly years. There would be no way to reduce the uncertainty. No telescope on Earth could see the rock. The question of whether the Moon was about to receive an asteroid strike would simply linger, unanswerable. The only instrument capable of resolving the question was, once again, the James Webb Space Telescope. In February of 2026, more than a year after the initial observations, Webb was aimed at the asteroid for a second time. The asteroid was now even farther away, even fainter, at the extreme limits of what the telescope could detect. ESA described the resulting observations as among the faintest ever observations of an asteroid in history. The challenge of detecting a 60-meter rock at that distance, distinguishing its feeble infrared glow from the noise of the cosmos, pushed Webb to its absolute operational limits. But it succeeded. The positional data from the 2026 observations, combined with all previous measurements, were sufficient to rule out a lunar impact definitively. 2024 YR4 would pass within approximately 21,200 kilometers of the Moon's surface. A near miss, but a miss. Neither Earth nor the Moon would be struck. The saga, from discovery on December 27, 2024, to final resolution in March of 2026, had lasted approximately 14 months. And in those 14 months, 2024 YR4 had exposed a vulnerability in the architecture of planetary defense that the community had long feared but never confronted in practice. The vulnerability is the gap between detection and certainty, the window of time during which a threat is known to exist but cannot be resolved. 2024 YR4 was discovered, tracked, escalated to the highest risk level in history, and then watched as it faded beyond the reach of ground-based astronomy. If the orbit had not been resolved before the asteroid vanished, the world would have faced years of unresolved uncertainty, years of knowing that a city-killing rock might be heading our way, but being unable to confirm or deny it. Years during which the lead time for a deflection mission would be steadily shrinking. Something is wrong with the assumption that the current system is adequate. 2024 YR4 was in nearly every respect a best-case scenario. It was found early enough to track. The world's most powerful telescope was available and capable of observing it, and the orbit turned out to be safe. But the margins were excruciatingly thin. If the asteroid had been discovered a month later, there might not have been time to resolve the orbit before it vanished. If the JWST had been occupied with other observations and unable to respond, the uncertainty might have persisted for 3 years. And if the orbit had turned out to be on a collision course, the lead time of roughly 8 years, while longer than many scenarios, might still have been insufficient for deflection. The next asteroid might not be this cooperative. The next one might arrive from the direction of the Sun, invisible to every telescope, like the Chelyabinsk meteor did in 2013. The next one might be darker, fainter, harder to find. The next one might give us less warning, or no warning at all. The story of 2024 YR4 is not a story of a crisis averted. It is a story of a rehearsal, a dress rehearsal for a performance that the universe will eventually demand for real. The story of 2024 YR4 did not unfold in isolation. It was the most dramatic test of a planetary defense system that had been under construction for decades. A system built piece by piece, mission by mission, failure by failure, and occasional triumph by triumph. To understand what the world could and could not do when confronted with a real threat, you have to understand the missions, the technologies, and the bitter lessons that built the architecture of planetary defense long before 2024 YR4 ever appeared in a Chilean telescope's datastream. The first chapter of that story begins not with defense, but with reconnaissance. Chapter 1. Spaceguard and the Great Census. In the early 1990s, the idea that asteroids posed a genuine, quantifiable threat to civilization was still, in many quarters, treated as fringe science. Yes, the evidence for the Chicxulub impact was mounting. Yes, the Shoemaker-Levy 9 collision with Jupiter in 1994 had been spectacular. But the notion that governments should spend real money to find and track every potentially dangerous rock in near-Earth space was a hard sell. The probabilities were low, the costs were uncertain, and the political will was thin. What changed the equation was a quiet, methodical effort by a small community of scientists, led by figures like astronomer Eugene Shoemaker, planetary scientist David Morrison, and later, Lindley Johnson, who would become NASA's first planetary defense officer. These advocates made a simple argument. The cost of finding the asteroids was trivial compared to the cost of being hit by one. A comprehensive survey of near-Earth objects larger than 1 kilometer, the size above which an impact could threaten civilization, would cost a fraction of a single space shuttle launch. The insurance value was incalculable. In 1998, Congress responded. The Spaceguard survey mandate directed NASA to find 90% of all near-Earth objects larger than 1 kilometer within 10 years. The telescopes that would carry out this mandate, the Catalina Sky Survey, Linear, Spacewatch, and later Atlas and Pan stars, began their systematic sweeps of the sky. By the mid-2000s, the catalogue of known near-Earth objects was growing rapidly. By 2008, the Spaceguard goal had been largely met. More than 90% kilometer-class near-Earth objects had been found, and none was on a collision course with Earth in the foreseeable future. This was, by any measure, a monumental achievement. Humanity had, for the first time in its history, looked out into the void and accounted for the objects large enough to destroy civilization. The existential threat from massive asteroid impacts had been, if not eliminated, then at least quantified and largely addressed. The chance of a surprise Chicxulub-class impact occurring without warning had been reduced to something very close to zero. But Spaceguard left a gap, a dangerous, yawning gap. It focused on kilometer-class objects, because those were the civilization enders. It did not address the far more numerous population of smaller objects, those in the 100 to 300 meter range, which could devastate entire regions, or those in the 50 to 100 meter range, the Tunguska-class city killers, which could destroy a metropolitan area. These smaller objects were harder to find, harder to track, and vastly more numerous. In 2005, Congress updated the mandate, directing NASA to find 90% of near-Earth objects larger than 140 meters by 2020. That deadline passed without being met. As of the mid-2020s, the search continues, with survey programs chipping away at the problem but facing fundamental limitations in telescope sensitivity and sky coverage. The numbers are striking. Of the estimated 25,000 near-Earth objects larger than 140 meters, roughly 10,000 have been found, about 40%. Of the hundreds of thousands of objects in the 50 to 100 meter class, only a tiny fraction have been catalogued. The population of city-killing asteroids remains, for the most part, invisible, 2024 YR4 was a member of that invisible population until the night it happened to drift through the field of view of an Atlas telescope. The lesson of the SpaceGuard era is both inspiring and sobering. We proved we could find the big ones. We proved that a systematic, funded, sustained effort could reduce an existential risk. But we also proved that the smaller threats, the ones that are more likely to affect any individual generation, remain largely unaddressed. The system that found 2024 YR4 was designed to find objects like it, but it found it almost by accident in the narrow window when the asteroid happened to be close enough and bright enough to detect. Had its orbit been slightly different, had it approached from a different angle, had the weather been poor over Chile that night, it might have passed unnoticed, only to return in 2032 with no warning at all. Chapter 2. The Chelyabinsk wake-up call. If the SpaceGuard era was the slow, methodical construction of a defense, the Chelyabinsk event of February 15, 2013, was the alarm that proved the defense had holes. On the morning of that day, a Friday, at approximately 9:20 local time, an asteroid roughly 20 meters in diameter entered Earth's atmosphere at a velocity of approximately 19 kilometers per second, about 12 miles per second. It came from the direction of the Sun, making it completely invisible to every detection system on the planet. No telescope saw it coming. No warning was issued. No sirens sounded. The first indication that anything was wrong was a flash of light brighter than the Sun, visible across hundreds of kilometers of the Ural Mountains region of Russia. The asteroid, a stony object likely classified as an ordinary chondrite, detonated in an airburst at an altitude of roughly 29.7 kilometers, approximately 18.5 miles above the city of Chelyabinsk, a city of more than 1 million people. The explosion released energy estimated at approximately 500 kilotons of TNT, roughly 30 times the yield of the Hiroshima bomb. The resulting shockwave, traveling outward at the speed of sound, took several minutes to reach the ground, giving people who had seen the flash time to move toward their windows to investigate exactly the wrong thing to do. When the shockwave arrived, it shattered windows across 6 cities, damaging more than 7,200 buildings. 1,500 people sought medical treatment for injuries, the vast majority caused by flying glass. Over 180 people reported eye injuries from the intense flash. 20 people suffered ultraviolet burns. The economic damage was estimated at more than $30 million. Nobody died. This fact is remarkable, and it is largely a matter of luck. The airburst occurred at high altitude, distributing the energy across a wide area rather than concentrating it on the surface. If the asteroid had been slightly larger, or slightly denser, or had entered the atmosphere at a steeper angle, it might have penetrated deeper before exploding, or even reached the ground. A ground-level impact in a city of 1 million people would have been catastrophic. The Chelyabinsk event carried multiple lessons, each more uncomfortable than the last. First, it demonstrated that objects in the 20-meter size class, well below the threshold of any existing survey, could cause significant damage and mass injuries. Second, it proved that objects could arrive completely without warning from the direction of the Sun, a blind spot that no ground-based telescope can cover. Third, and most importantly, it arrived on the same day that astronomers were closely tracking asteroid 2012 DA14, a much larger object that was making a close approach to Earth. The global astronomical community was watching one rock when another rock, unrelated and undetected, struck the planet. The irony was painful. It was as if a security guard, binoculars pressed to his eyes and watching a suspicious figure across the street, had been hit in the back of the head by a burglar climbing through the window behind him. The Chelyabinsk event accelerated the development of planetary defense as a policy priority. In 2016, NASA established the Planetary Defense Coordination Office, or PDO, to oversee all aspects of asteroid detection, tracking, and response. Lindley Johnson, who had been advocating for planetary defense for decades, was appointed its first officer. The PDCO became the institutional home for a function that had previously been scattered across multiple NASA programs. It was a small office with a modest budget, but its existence sent a signal. The United States government now treated asteroid impacts as a formally recognized hazard requiring an organized response. But detection, no matter how good, solves only half the problem. The other half is deflection. Finding the asteroid is necessary. Changing its course is the goal. And in the years between Chelyabinsk and the discovery of 2024 YR4, the world made its first attempt at actually moving an asteroid. Chapter 3. DART and the first deflection. The double asteroid redirection test, known as DART, was the most audacious planetary defense mission ever attempted. Its premise was simple: slam a spacecraft into an asteroid and see if you can change its orbit. Its execution was anything but simple. The target was Dimorphos, a small moonlet, approximately 160 meters in diameter, orbiting a larger asteroid called Didymos. The Didymos-Dimorphos system is a binary asteroid, two objects gravitationally bound to each other, with Dimorphos orbiting Didymos roughly once every 11 hours and 55 minutes. The system was chosen because the orbital period of Dimorphos could be measured from Earth by timing the slight dip in brightness that occurs each time Dimorphos passes in front of or behind Didymos. Any change in Dimorphos's orbit caused by the DART impact would show up as a change in this orbital period, a change that could be measured with high precision from hundreds of millions of kilometers away. The DART spacecraft was built by the Johns Hopkins University Applied Physics Laboratory and launched on November 24, 2021, aboard a SpaceX Falcon 9 rocket from Vandenberg Space Force Base in California. It traveled for 10 months through interplanetary space, navigating by the stars, homing in on its target, using an autonomous guidance system called SmartNav. In the final hours of approach, SmartNav took over entirely, identifying Dimorphos, locking onto it, and steering the spacecraft toward a direct hit. No human controller could react fast enough to guide the spacecraft in those final moments. The round-trip light delay between Earth and the spacecraft was too long. DART had to find and hit its target on its own. On September 26, 2022, at 23:14 Coordinated Universal Time, DART struck Dimorphos at a velocity of roughly 6.6 kilometers per second, approximately 14,000 miles per hour. The spacecraft weighed roughly 580 kilograms at impact, about the mass of a grand piano. Dimorphos weighed roughly 5 billion kilograms. The mass ratio was absurd, like throwing a mosquito at a freight train, and yet the impact worked. The collision shortened Dimorphos' orbital period by 32 minutes, from 11 hours and 55 minutes to 11 hours and 23 minutes. The predefined success threshold had been a change of at least 73 seconds. DART exceeded that threshold by a factor of more than 25. The reason for this outsized effect was one of the most important findings of the mission. The impact kicked up an enormous cloud of debris from Dimorphos's surface, and the recoil from that ejected material amplified the momentum transfer far beyond what the spacecraft alone could have delivered. Scientists calculated a momentum enhancement factor, called beta, of roughly 3.6, meaning the total momentum imparted to Dimorphos was nearly 4 times what the spacecraft had contributed directly. The debris did more work than the spacecraft itself. Images from the DART spacecraft's camera, which transmitted data right up until the moment of impact, revealed Dimorphos to be a rubble pile asteroid, a loose collection of boulders held together by gravity rather than a single solid rock. This finding was consistent with other rubble pile asteroids studied by spacecraft, including Ryugu and Bennu. It meant that Dimorphos was structurally weak, which explained the large amount of debris ejected by the impact. It also meant that future deflection attempts against similar objects might be even more effective than expected. The DART mission was a triumph. It was the first time in the history of civilization that humanity had deliberately and measurably altered the orbit of a celestial body. The implications for planetary defense were profound. Kinetic impact, the simplest and most intuitive method of asteroid deflection, had been proven to work. If a threatening asteroid were discovered with sufficient lead time, a spacecraft could, in principle, be launched to collide with it and change its trajectory enough to convert a hit into a miss. The key variable was time. The earlier the deflection was applied, the smaller the velocity change needed, because even a tiny nudge, applied years in advance, would accumulate into a large positional shift by the time the asteroid reached Earth's orbit. The math is striking. A velocity change of just 1 centimeter per second, applied 10 years before impact, could shift the asteroid's position at the time of the encounter by thousands of kilometers, more than enough to convert a direct hit into a clean miss. But that same 1 centimeter per second change, applied 1 year before impact, would shift the position by only a few hundred kilometers. Applied 1 month before impact, it would shift the position by only a few tens of kilometers, possibly not enough to avoid a strike. The effectiveness of deflection is directly proportional to the lead time. Every month of delay reduces the margin of safety. Every year of uncertainty narrows the window. And every gap in observation, every period when the asteroid is invisible and untrackable, is time that cannot be recovered. This is exactly the vulnerability that 2024 YR4 exposed. The asteroid was discovered roughly 8 years before the potential impact date. 8 years might sound like a generous margin, but by the time the orbit was characterized well enough to confirm the threat, several weeks had already been consumed. The DART mission, from formal proposal to impact, had taken roughly 7 years. A deflection mission for 2024 YR4, launched at the point when the threat was at its highest in February of 2025, would have had roughly 7.5 years, barely enough assuming the mission could be designed, built, and launched on an accelerated timeline. And if the orbit had not been resolved until the asteroid reappeared in 2028, the remaining lead time would have been only 4 years. That might not have been enough. Chapter 4. The Neo Surveyor and the Search for the Invisible. Even as the saga of 2024 YR4 was unfolding, another critical piece of the planetary defense architecture was being prepared for launch. The Near-Earth Object Surveyor, or NEO Surveyor, is a space telescope designed specifically to find the asteroids that ground-based surveys cannot see. Ground-based telescopes have a fundamental limitation. They can only observe at night, and they cannot see objects near the Sun. Asteroids that approach Earth from the sunward direction, like the Chelyabinsk meteor, are invisible to ground-based observers because they are lost in the Sun's glare. This blind spot is not a technical failure. It is a geometric fact. The Sun illuminates the daylight sky so brightly that faint objects near it cannot be detected from the ground, no matter how large or how close. NEO Surveyor is designed to circumvent this limitation. It will operate in infrared wavelengths, detecting asteroids by the heat they emit rather than the sunlight they reflect. Because it will observe from space, it will not be limited by the day-night cycle or by atmospheric interference. Its planned orbit, at the first Sun-Earth Lagrange point roughly 1.5 million kilometers sunward of Earth, will give it a vantage point from which to observe regions of the sky that are perpetually inaccessible to ground-based telescopes. The mission's goal is ambitious: to find at least 2/3 of the remaining population of near-Earth objects larger than 140 meters within 10 years of launch. If successful, NEO Surveyor would dramatically reduce the size of the uncharted population of potentially hazardous asteroids, closing the gap that has existed since the SpaceGuard era. It would also provide early detection of smaller objects, including objects in the 50 to 100 meter class, like 2024 YR4, that might otherwise go unnoticed until they were dangerously close. But NEO Surveyor has faced repeated delays and budget pressures. Its development timeline has been extended multiple times, and while it remains a high priority within NASA's planetary defense portfolio, it has yet to reach space. The telescope that caught 2024 YR4 was not NEO Surveyor. It was Atlas, a ground-based system with all the limitations of ground-based systems. And the telescope that resolved the crisis was the James Webb Space Telescope, a general-purpose observatory that was never designed for this task and cannot be routinely used for planetary defense. The lesson is clear. The tool that would have been most useful during the 2024 YR4 crisis, a space-based infrared survey telescope dedicated to finding and tracking near-Earth objects, does not yet exist in operational form. The world managed the crisis with the tools it had. but the tools it had were not the tools it needed. Chapter 5. The Human Element and the Problem of Warning. There is a final chapter in the exploration of what humanity tried and learned during the 2024 YR4 episode, and it is not about telescopes or spacecraft or orbital mechanics. It is about communication, about what you tell people when you find a rock that might destroy one of their cities, about how you deliver that message, and about what happens when the message is heard. Throughout the crisis, scientists and space agencies faced a delicate balancing act. The impact probability was real, elevated, and historically unprecedented. It could not be ignored, and it would not have been responsible to conceal it. The data were public, posted on the Sentry risk table for anyone to read. Journalists were watching. Social media amplified every update. Each new revision of the impact probability was reported, often with headlines that emphasized the danger over the context. At the same time, the most likely outcome, even at the peak of the crisis, was a miss. The probability never exceeded 3.1%. That meant there was a 96.9% chance that the asteroid would pass safely. The challenge was communicating both realities simultaneously. Yes, there is a risk, and yes, the most likely outcome is safe. David Rankin of the Catalina Sky Survey struck this balance with characteristic clarity throughout the crisis. People should absolutely not worry about this yet, he told Space.com in late January of 2025, when the probability was still around 1%. Impact probability is still very low, and the most likely outcome will be a close approaching rock that misses us. He predicted, correctly, that the probability would eventually drop to zero as more data came in. But he also acknowledged the uncertainty, noting that the orbit was still too imprecise to be definitive, and that the situation would remain unresolved until more observations could be gathered. Not every voice was as measured. Some media reports focused on worst-case scenarios. Some public figures issued dramatic warnings that, while technically accurate, lacked the context necessary for a calm assessment. Neil deGrasse Tyson, the astrophysicist and science communicator, publicly discussed the asteroid's potential to be a city killer, a phrase that was accurate but alarming when stripped of the 97% probability of a miss. The tension between informing the public and alarming the public is one of the hardest problems in risk communication, and it becomes especially acute when the risk involves low probability, high consequence events. A 3% chance of a city being destroyed is, by any rational measure, a significant risk, but it is also a 97% chance of nothing happening at all. How do you communicate that? How do you ensure that the public takes the risk seriously without causing panic? And how do you maintain credibility when, as in this case, the risk ultimately resolves to zero? The danger is that the next time a similar threat is announced, the public will remember the false alarm and dismiss the warning, even if the next time the threat is real. The 2024 YR4 episode provided no definitive answers to these questions, but it provided a wealth of real-world experience. It demonstrated that the existing communication protocols, built around the Torino Scale, the Sentry risk table, and the ION notification system, functioned as designed. It showed that scientists could communicate uncertainty honestly without triggering mass panic, and it highlighted the need for continued investment in public education about asteroid risks, so that when the next alert comes, and it will come, the public will have the context to understand what the numbers mean. The lessons of these 5 chapters, SpaceGuard, Chelyabinsk, DART, Neo-Surveyor, and the challenge of communication, converge on a single, uncomfortable truth. Humanity has built the foundation of a planetary defense system. It can detect many, though not all, threatening objects. It has proven, with DART, that it can deflect an asteroid if given enough time. It has created institutional structures, from CNEOs to ION to the PDSO, to coordinate a global response. But the system has gaps, serious gaps. Gaps in detection, gaps in lead time, gaps in deflection readiness, and gaps in public communication. 2024 YR4 did not exploit those gaps. The next asteroid might. It is late now. The numbers have been laid out, the timelines reconstructed, the missions examined, the probabilities calculated, escalated, and finally resolved. The immediate story of 2024 YR4 has an ending, and the ending is reassuring. The rock will miss. Earth is safe. The moon is safe. The crisis is over. And for the vast majority of people who followed the story, that is where the narrative ends, with a sigh of relief and a return to normal life. But sit with this story a little longer, because underneath the reassurance, underneath the resolved probabilities and the triumphant declarations of impact probability 0, there is a deeper truth. And it is a truth that, once you see it, changes the way you look at the night sky. Here is the first part of that truth. 2024 YR4 was not special. It was ordinary. In every measurable way, it was a typical member of the vast population of near-Earth objects that share our orbital neighborhood. A stony asteroid, roughly 60 meters across, on a 4-year orbit around the Sun, with a rotation period of about 19.5 minutes. There are thousands of objects like it. Tens of thousands, possibly hundreds of thousands. Most of them have never been seen by any telescope. Most of them are right now, at this very moment, moving silently through the darkness on orbits that are unknown to anyone. Some of those orbits cross Earth's path, and some of those crossings will, eventually, result in a collision. This is not speculation, it is statistical certainty. The impact rate for objects in the 50 to 100 meter size class is estimated at roughly once every several hundred to 1,000 years. The Tunguska event occurred in 1908. The Chelyabinsk meteor, though smaller, struck in 2013. The intervals between events of this scale are measured in human lifetimes, not geological epochs. Somewhere in the solar system, right now, there is an asteroid that will, at some future date, strike Earth. We do not know its name. We do not know its orbit. We may not have discovered it yet. But the laws of probability and the mechanics of orbital dynamics guarantee its existence. The second part of the deeper truth is more unsettling still. The system we have built to protect ourselves is incomplete, and the incompleteness is not a matter of minor gaps or marginal deficiencies. It is fundamental. Consider the numbers. There are an estimated 25,000 near-Earth objects larger than 140 meters. Fewer than half have been found. There are hundreds of thousands of objects in the 50 to 100 meter range, the city killers. Only a small fraction have been catalogued. The survey programs, Atlas, Catalina, Pan-STARRS, are remarkable instruments, each one a triumph of engineering and persistence. But they operate on the ground, which means they are limited to nighttime observation. They cannot see objects that approach from the direction of the sun. They are blinded by weather, by moonlight, by atmospheric turbulence, and they are searching for objects that are, by definition, small, faint, and fast-moving, objects that are often visible only when they are already dangerously close. The NEO-Surveyor mission, when it launches, will address some of these limitations, but it is one telescope, with a finite field of view, operating for a limited mission duration. It will find many asteroids. It will not find them all. And even when an asteroid is found, tracking it continuously is another matter entirely. 2024 YR4 was found. It was tracked for a few months, and then it vanished, fading beyond the reach of ground-based telescopes, leaving behind an unresolved probability of lunar impact that persisted for a year. The observation gap, the period during which the asteroid was invisible and untrackable, was one of the most nerve-wracking features of the entire episode, and it is a feature that will recur again and again for any asteroid with an orbit that carries it into the outer reaches of the inner solar system between close approaches. The third part of the deeper truth concerns time. Time is the most precious resource in planetary defense, and it is the one resource that is always in shorter supply than we would like. The DART mission demonstrated that kinetic impact can deflect an asteroid, but DART took 7 years from concept to execution, and it targeted an asteroid that was not actually threatening Earth, an asteroid whose orbit, composition, and physical properties were well characterized long before the spacecraft was launched. A real-world deflection mission against a newly discovered threat would face far greater uncertainties. The asteroid might be a rubble pile, like Dimorphos, or it might be a solid monolith. It might be spinning slowly, or tumbling chaotically. It might be accompanied by smaller fragments. Each of these variables affects the design of the deflection mission, and each of these variables might not be known until the spacecraft arrives, by which point the mission is already committed. If 2024 YR4 had turned out to be on a collision course, the world would have had roughly 8 years to respond. 8 years sounds like a lot, but consider what those 8 years would have required. First, a definitive confirmation that the asteroid was actually on an impact trajectory. A confirmation that, as we have seen, might not have been possible until the asteroid reappeared in 2028, leaving only 4 years. Second, the design and construction of a deflection spacecraft, a process that typically requires at least 3 to 5 years. Third, the launch and transit of the spacecraft, which could take months to years depending on the trajectory. Fourth, the actual deflection event, followed by verification that the orbit had been changed sufficiently. The timeline is brutally tight. There is no room for delays, for budget overruns, for launch failures, for any of the 1,000 things that routinely go wrong in the development of complex space missions. And the timing problem gets worse for smaller objects. 2024 YR4 was discovered roughly 8 years before its potential impact, but the Chelyabinsk meteor was discovered 0 seconds before impact. It arrived without warning. The Tunguska object arrived without warning. Many of the most dangerous asteroids approach from directions that are difficult to observe, pass through the inner solar system quickly, and provide windows of detectability measured in weeks or months, not years. For these objects, the concept of deflection is moot. There is no time to deflect them. The only options are detection and civil defense, finding them, calculating where they will hit, and evacuating the impact zone. And for the smallest, fastest, most difficult to detect objects, even that may not be possible, this is not science fiction. This is the operational reality of living on a planet that orbits within a debris field. The night sky, to the naked eye, looks serene, unchanging, eternal. The stars burn steadily. The moon traces its familiar arc. The planets wander slowly among the constellations. But this serenity is an illusion created by the limitations of human perception. The solar system is a dynamic, violent, hazardous environment. Objects collide, surfaces are scarred, orbits shift, and Earth, for all its apparent tranquility, for all the comfort of its blue sky and its breathable atmosphere, is not exempt from the violence. It never has been. It is shielded by nothing more than a thin envelope of air that, while effective against small impactors, is entirely inadequate against objects above a certain size. An asteroid 50 meters across will punch through the atmosphere and deliver its energy to the surface or to the lower atmosphere with devastating efficiency. An asteroid 100 meters across will excavate a crater. An asteroid 1 kilometer across will alter the climate. An asteroid 10 kilometers across will end civilization. Every atom in your body was forged inside a dying star. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was synthesized in the nuclear furnaces of stars that burned and exploded billions of years before the Earth formed. You are made of stardust, as the saying goes, but stardust is just another way of saying debris. You are made of the same material as the asteroids, the same silicon, the same iron, the same primordial stuff that was left over from the formation of the solar system. The rocks that threaten Earth are, in a very real sense, your distant cousins, fragments of the same disk of gas and dust that gave birth to your planet, your atmosphere, and ultimately, to you. Let that sink in. The threat is not external. It is not alien. It is a natural consequence of living in the solar system that made you. The same processes that created the Earth also created the asteroids that might one day destroy the cities built upon it. The same gravity that holds you to the surface of the planet also tugs on rocks millions of kilometers away, pulling them onto trajectories that might, over the eons, cross your path. The universe does not distinguish between the matter that thinks and the matter that falls. It treats both with perfect indifference. There is a philosophical weight to this realization that goes beyond the specific details of 2024 YR4. The asteroid itself was ordinary. Its orbit was ordinary. Its composition was ordinary. What was as extraordinary was the brief window of time during which its ordinariness intersected with human awareness. For a few weeks in January and February of 2025, a rock that had been orbiting the Sun for billions of years, unseen, untracked, unknown, became the most closely watched object in the solar system. Hundreds of astronomers turn their telescopes toward it. Millions of people read about it. The most powerful observatory ever built was redirected to observe it. And then the crisis passed, the probability dropped to zero, and the world moved on. But 2024 YR4 did not move on. It is still out there, right now, orbiting the Sun on its 4-year path, tumbling slowly through the void, a 60-meter rock with a 19.5-minute rotation period, indistinguishable from any other small, stony asteroid in the inner solar system. It will return to Earth's vicinity in late 2028. It will make its closest approach in December of 2032, passing within roughly 21,000 kilometers of the Moon. And then it will continue on, looping back out toward the asteroid belt, only to return again and again and again, for as long as the solar system endures, or until the slow perturbations of Jupiter's gravity finally redirect its orbit, or until, millions or billions of years from now, it collides with something. The universe is patient. It has time. It has unimaginable quantities of time. We do not. A human civilization that has existed for roughly 10,000 years, that has developed written language for only about 5,000, that has possessed the ability to detect incoming asteroids for barely 30. This civilization occupies a sliver of time so thin that it is essentially invisible on the cosmic scale. If the 4.6 billion year history of the solar system were compressed into a single year, human civilization would have existed for the final 200ths of a second before midnight on December 31st. And the era of planetary defense, the period during which we have had any ability whatsoever to detect and respond to asteroid threats, would have lasted for less than 1,000th of a second. We are a flicker of awareness in a cosmos that has been raining rocks on this planet for longer than we can meaningfully comprehend. And yet, in that flicker, we built something remarkable. We built telescopes that can detect a 50-meter rock at tens of millions of kilometers. We built algorithms that can calculate, to multiple decimal places, the probability of a collision years in the future. We built a spacecraft that flew to an asteroid and changed its orbit. We built institutions and protocols and communication networks to coordinate a global response. We did all of this in less than 3 decades, starting from essentially nothing. The speed of that achievement is, by any fair assessment, extraordinary. The question is whether it is fast enough. There is a thought experiment that planetary defense scientists sometimes use to convey the stakes. Imagine you are standing on a highway at night. You are wearing dark clothing. Cars are approaching at high speed, their headlights visible in the distance. Some of those headlights will pass by you, their beams sweeping the roadside without touching you. But statistically, inevitably, one of those cars will be on a trajectory aimed directly at where you are standing. The question is not whether it will happen. The question is when. And the question is whether you will see the headlights in time to step aside. Right now, humanity is standing on that highway. We have built a few floodlights to illuminate the road in front of us. Atlas, Catalina, Pan-STARRS, they are our floodlights. They illuminate a large area, but not all of it. There are blunt blind spots toward the sun, below the horizon, in the glare of the full moon. And the objects approaching us are not all equally visible. The big ones, the kilometer-class civilization enders, shine brightly in our floodlights and have largely been accounted for. The medium ones, 100 to 300 meters, are dimmer but detectable with effort. But the small ones, the 50 to 100 meter city killers, the Tunguska-class impactors, those are faint, fast, and often visible only when they are already dangerously close. 2024 YR4 appeared in our floodlights just barely, just in time, just bright enough. The next one might not. There is a deeper irony in this story that deserves attention. Humanity has built spacecraft that have visited asteroids, orbited them, landed on them, collected samples from their surfaces, and returned those samples to Earth. The OSIRIS-REx mission brought back material from asteroid Bennu. The Hayabusa 2 mission returned samples from asteroid Ryugu. These are extraordinary achievements, representing the pinnacle of robotic space exploration. We have touched asteroids. We have tasted their chemistry. We have mapped their surfaces at centimeter resolution. And yet, We cannot reliably find a 50-meter rock heading toward us with less than a few weeks of warning. The disconnect between what we can do and what we routinely fail to do is not a contradiction. It is a consequence of priorities. The missions that visit asteroids are funded through NASA's Science Directorate. The programs that find threatening asteroids are funded through the Planetary Defense Budget. The two budgets are separate. The two communities, while overlapping, have different goals, and the Planetary Defense Budget, while growing, remains a small fraction of the total spent on space science and exploration. During the 2024 YR4 crisis, this tension became acute. The James Webb Space Telescope, a science instrument costing roughly $10 billion, was diverted from its primary mission to observe an asteroid. The observations were valuable, arguably essential for resolving the crisis, but the JWST cannot be routinely used for planetary defense. It has a packed observation schedule, driven by the demands of its science community. Every hour spent looking at an asteroid is an hour not spent studying the early universe or characterizing exoplanet atmospheres. The emergency use of JWST during the 2024 YR4 crisis was a testament to the flexibility and responsiveness of the astronautical community. It was also a reminder that the world does not yet have a dedicated space-based asset for planetary defense observation. The Vera C. Rubin Observatory, a ground-based survey telescope under construction in Chile, with an 8.4-meter mirror and a 3.2 gigapixel camera, the largest digital camera ever built, is expected to begin operations in the mid-2020s. Its legacy survey of space and time, a 10-year mapping project that will survey the entire visible southern sky every few nights, is projected to discover tens of thousands of new near-Earth objects, including many in the smaller size classes that have so far eluded detection. The Rubin Observatory may well represent the single most significant advance in asteroid detection since the SpaceGuard era. But even Rubin, with its extraordinary capabilities, will remain a ground-based instrument, subject to the same limitations of weather, daylight, and solar direction blind spots that affect all ground-based telescopes. The cold truth is this: humanity has made extraordinary progress in planetary defense in a very short time. But the progress is incomplete. The tools we have are not yet sufficient. The institutional frameworks are young, the budgets are modest, and the adversary, if we can call the cosmic impact hazard an adversary, is patient, relentless, and operates on timescales that dwarf the entire span of human civilization. We have achieved a great deal. We have not yet achieved enough, and the universe does not grade on a curve. But perhaps the most important insight from the deeper truth of 2024 YR4 is not about technology at all. It is about awareness, about the strange, vertiginous experience of knowing with scientific precision that you live on a target. Before the modern era of planetary defense, cosmic impacts were, for most people, matters of ancient history or science fiction. The dinosaur-killing asteroid was a fascinating fact about the distant past. Asteroid impact movies were entertaining but not personally relevant. The notion that a rock from space might, within your own lifetime, destroy the city where you live was so remote from daily experience that it barely registered as a concern. The threat was abstract, theoretical, belonging to the realm of could happen but probably won't, filed alongside supervolcano eruptions and nearby supernova explosions and all the other low probability, high-consequence events that the human mind is poorly equipped to process. 2024 YR4 changed that. For a few weeks, the threat was not abstract. It had a name, a number, a size, a date, and a list of cities in the potential impact corridor. People in Bogota, Lagos, Mumbai, and Dhaka could look at a map and see the risk corridor crossing their homes. The probability was not theoretical. It was published, updated daily, and trending upward. The question was not whether an asteroid could hit Earth. It was whether this specific asteroid would hit these specific places on this specific date. The abstraction collapsed into something immediate, personal, and frightening. And then the threat resolved. The probability dropped to zero. Life returned to normal. The asteroid faded from the news, replaced by the next story, the next crisis, the next distraction. But the knowledge remains. The knowledge that the solar system is a place where rocks fall, where orbits intersect, where the calm surface of daily life rests on a platform of cosmic contingency that could, at any moment, be disrupted by an event that no human action can prevent, only detect, prepare for, and, if we are fortunate, deflect. This knowledge is, in a sense, a gift. It is the gift of perspective. The gift of understanding that the most important project in the history of the human species is not the construction of buildings or the accumulation of wealth or the prosecution of wars. It is the survival of the species itself. And survival, in a solar system that regularly flings rocks at inhabited planets, requires vigilance, investment, and a long-term commitment to watching the sky with instruments that most people will never see and understanding orbits that most people will never compute. The story of 2024 YR4 is a story about a rock that nearly hit us, that turned out to miss, that was tracked by a global network of telescopes and resolved by the most powerful observatory in space. But it is also a story about the fragility of the system that tracked it, the gaps that nearly allowed the threat to go unresolved, and the uncomfortable reality that the next rock might not be so obliging. Consider for a moment the Chelyabinsk meteor one more time. 20 meters, one-third the size of 2024 YR4, undetected. It came from the direction of the sun. 1,500 people were injured. 7,200 buildings were damaged. If that rock had been 60 meters across instead of 20, the energy released would have been roughly 27 times greater, not a broken windows event, a destroyed buildings event, a destroyed neighborhoods event, possibly a destroyed city event, depending on the altitude of the airburst and the density of the population below. And nobody saw it coming, not Atlas, not Catalina, not Pan-STARRS, not CNEOS, not NEOCC, not any institution or instrument anywhere on Earth. It arrived in complete silence and announced itself with a flash that blinded drivers and a shockwave that hospitalized hundreds. That is the gap. That is the vulnerability. That is the deeper truth that 2024 YR4 illuminated but did not by itself resolve. We are temporary patterns in matter and energy, briefly complex enough to understand the threats we face, briefly capable enough to build the tools that might save us, and briefly aware enough to know that the tools are not yet finished. That awareness, uncomfortable as it is the most valuable thing the story of 2024 YR4 leaves behind. More valuable than the orbital calculations, more valuable than the web images, more valuable than the Sentry risk tables. The awareness that we are not finished, that the work of planetary defense is not a completed project but an ongoing one, requiring sustained attention, sustained funding, and sustained will across generations, across political cycles, across the short attention span rhythms of modern life. The next asteroid is already out there. It has been orbiting the sun for billions of years, as patient and indifferent as the cosmos itself. It does not know about us. It does not care about our cities, our civilizations, our children. It is a rock, following the laws of physics, and it will go where those laws send it, whether we see it coming, whether we are prepared, whether we have the tools and the time to respond. That is entirely up to us. There is one more dimension to the deeper truth that warrants exploration, and it concerns the nature of the threat itself. Asteroids are not earthquakes. They are not volcanic eruptions. They are not hurricanes or tsunamis or pandemics. Every other natural disaster that humanity faces is fundamentally unpredictable at long timescales. We cannot say, with any confidence, where the next major earthquake will occur 10 years from now, or when the next supervolcano will erupt. We can identify areas of elevated risk, but we cannot forecast specific events years in advance. Asteroids are different. They obey Newton's laws with exquisite precision. Their orbits, once determined, can be projected forward for centuries with remarkable accuracy. This means that an asteroid impact is, at least in principle, the only natural disaster that can be predicted years or decades before it occurs. And if it can be predicted, it can, at least in principle, be prevented. No other natural disaster offers this possibility. We cannot stop an earthquake. We cannot prevent a volcanic eruption. We cannot steer a hurricane. But we can, with sufficient warning and sufficient technology, deflect an asteroid. The DART mission proved it. The physics works. The engineering works. The only questions are whether we will see the asteroid in time and whether we will have the resources to respond. This is what makes the story of 2024 YR4 so significant. It was not a disaster. It was a test that the system largely passed, but that also exposed critical weaknesses. The detection worked, the tracking worked, the risk assessment worked. The emergency deployment of JWST worked. But the margins were thin, the communication was imperfect, and the observation gap nearly left the world in years-long limbo. The test revealed that the system is functional but fragile, capable but incomplete, sufficient for this particular rock, at this particular time, but potentially insufficient for the next one. Lindley Johnson, NASA's planetary defense officer, once said something that captures the essence of this situation with elegant simplicity. A collision of a near-Earth object with Earth is the only natural disaster we now know humanity could completely prevent. The key word in that sentence is could, not will, not has, could. The capability exists in principle. Whether it exists in practice depends on investments, decisions and commitments that have not yet been fully made. The 2024 YR4 episode demonstrated, more powerfully than any simulation or exercise, what those investments, decisions and commitments need to look like. A dedicated space-based infrared survey telescope, like NEO-Surveyor, operational and scanning the sky continuously for objects approaching from every direction, including the sunward blind spot. A standing deflection capability, with spacecraft designs ready to build on short notice, launch vehicles available, and mission plans pre-computed for a range of asteroid sizes and orbits. An international framework for decision-making, agreed upon in advance, so that when the next high-probability threat is detected, the response does not have to be improvised from scratch, and a sustained, long-term commitment to funding and maintaining these capabilities, not as a one-time project, but as a permanent feature of human civilization, as essential as flood barriers and earthquake-resistant buildings and pandemic preparedness plans. We know what to do. We have seen what happens when we do not do it. The question is whether we will act before the next test becomes a final exam. The night sky is beautiful. It is vast and deep and full of wonders that have captivated human beings since we first looked up and asked what those points of light meant. But beauty does not mean safety. The cosmos is not a garden, it is a wilderness, and in a wilderness the price of inattention is not merely inconvenience, it is annihilation. 2024 YR4 came and went. It will return, as all asteroids on crossing orbits eventually return, looping back through the inner solar system on its 4-year cycle. It will pass close to the Moon in 2032, close enough to be a spectacular observational target, far enough to be harmless, and then it will recede again, back out toward the belt, back into the darkness, one small rock among millions, unremarkable and unseen, until the next time it catches the light of the sun and the gaze of a telescope. But the lesson it taught remains. The universe is not static, the sky is not empty, and the thin shell of air that protects this planet, the only planet we know of where anything lives, where anything thinks, where anything looks up and wonders, that thin shell is the only thing standing between us and the same fate that befell the dinosaurs, the Tunguska forest, and the windows of Chelyabinsk. We are not powerless, we have proven that, but we are not yet prepared, and the difference between those two statements is the difference between survival and catastrophe. There is a scale comparison that captures the absurdity of the planetary defense challenge in a way that numbers alone cannot. Imagine that the Earth is a basketball. At that scale, the Moon would be a tennis ball, orbiting about 7.5 meters away. The Sun would be a sphere, roughly 8 meters in diameter, sitting about 2.5 kilometers from the basketball. And 2024 YR4, the highest risk asteroid in history, the rock that commanded the attention of every space agency on Earth, the object that the James Webb Space Telescope was diverted to observe, would be a grain of sand too small to see without a magnifying glass. The entire crisis, the worldwide alarm, the formal notifications to governments, the emergency telescope time, the news coverage, the public anxiety, all of it was caused by a particle of dust, invisibly small against the scale of the solar system, carrying enough energy to flatten everything within a 50-kilometer radius. This disparity between the size of the threat and the magnitude of the consequences is one of the defining features of the asteroid impact hazard. The objects are tiny, the energies are colossal. A 50-meter rock, weighing perhaps 200,000 metric tons, traveling at 20 kilometers per second, carries kinetic energy proportional to the square of its velocity. The energy scales with mass and with the square of speed, which means that even a modest increase in velocity produces a dramatic increase in destructive potential. At typical asteroid encounter velocities, the kinetic energy of a 50-meter rock exceeds the yield of a large thermonuclear weapon. The rock does not need to be explosive. It does not need to carry a warhead. Its velocity alone is the weapon. The kinetic energy of its motion, accumulated over billions of years of orbital mechanics, is converted into heat, light, shock, and destruction in a fraction of a second upon impact. And we cannot see these objects until they are close. That is the fundamental paradox. The very quality that makes them dangerous, their small size, is also the quality that makes them hard to find. A 50-meter asteroid at a distance of 100 million kilometers has an apparent brightness comparable to a candle flame seen from the distance of the Moon. It is by any measure an extraordinarily faint target. The telescopes that hunt for these objects are, in effect, searching for candle flames at lunar distances, distinguishing them from the background glow of millions of stars, tracking their motion across the sky, and computing their future trajectories with enough precision to determine whether they will pass safely by or strike the planet. The engineering achievement is staggering. The fact that it works at all is a testament to human ingenuity. The fact that it does not yet work well enough is a testament to the scale of the challenge. The timeline of the 2024 YR4 crisis offers a granular view of how this challenge unfolds in practice. On December 27, 2024, the asteroid was discovered. On December 28, the Minor Planet Center published its initial orbit. On January 4, 2025, the Sentry system at CNEOS flagged the asteroid with an impact probability above 1% and placed it at the top of the risk table. Over the next 6 weeks, as observations accumulated from Atlas, Catalina, Pan-STARRS, and the Gemini South telescope, the impact probability rose steadily, from 1.2 to 1.3 to 2.1 to 2.6 to 3.1%. The International Asteroid Warning Network issued its formal notification on February 11th. The JWST observations were conducted on February 18th and 26th, and on February 23rd, the impact probability dropped to 0. That is a total elapsed time of 58 days from discovery to resolution. 58 days during which a city-killing rock held the highest risk rating in history. 58 days during which the world's planetary defense systems were tested, for the first time, against a genuine threat. In those 58 days, the system performed well, but it was pushed to its limits. The asteroid was fading fast, and ground-based telescopes were losing it. Without the JWST, the resolution might have been delayed by years. Without the ION protocols, the international response might have been chaotic and uncoordinated. Without the Sentry system and the Torino Scale, the public communication might have been confusing and contradictory. Every one of these components had been designed, built, and tested for exactly this kind of scenario, and every one of them was necessary. Remove any single element, the detection network, the risk assessment system, the space telescope, the international coordination framework, and the outcome might have been very different. Not necessarily worse in terms of the asteroid's actual trajectory, which was always going to miss Earth, but worse in terms of our ability to determine that it would miss, and worse in terms of the public's ability to understand what was happening. The fragility of the system is most apparent when you consider the role of the JWST. Webb was not built for this. It was not designed for this. It was not budgeted for this. Its emergency use during the crisis was the equivalent of borrowing a neighbor's car because yours broke down. It worked, but it is not a sustainable solution. The next time a similar crisis occurs, the JWST might be pointed at a distant galaxy and unable to respond. It might be undergoing maintenance. It might have exhausted its fuel supply and ceased operations. The fact that the most critical observation in the history of planetary defense was performed by a telescope that is not a planetary defense instrument should be a cause for concern, not comfort. The system needs redundancy. It needs depth. It needs instruments that are designed for this mission and dedicated to this mission, not borrowed from other purposes in moments of crisis. And those instruments need to be in space, where they can observe the entire sky, including the sunward blind spot, continuously, without interruption, for as long as the threat exists, which is to say, forever. Because the threat does not have an expiration date. It does not diminish over time. It is a permanent feature of the environment in which we live. The asteroid population of the inner solar system is continuously replenished by gravitational interactions with Jupiter and by collisions within the main belt. New objects enter near-Earth space on timescales of millions of years, replacing those that are lost to impacts, ejections, and orbital decay. The flux of potentially hazardous objects is, on human timescales, essentially constant. The danger that existed in 1908 at Tunguska, the danger that existed in 2013 at Chelyabinsk, the danger that materialized as a 3.1% impact probability in February of 2025, that danger will exist tomorrow and next year and 1,000 years from now. It is woven into the structure of the solar system itself, and the only way to live safely within that structure is to watch constantly, carefully, systematically, with the best instruments we can build and the most sustained commitment we can muster. To watch not because watching alone can stop a rock, but because watching is the first step, the essential precondition for everything that might follow, the deflection, the evacuation, the survival. 2024 YR4 taught us that the watch is working, and it taught us that the watch is not yet good enough. Both of those lessons matter. Both of them need to be remembered, because the next rock is already on its way. And there is one more truth that should be spoken, not because it is comfortable, but because it is necessary. The resolution of the 2024 YR4 crisis was celebrated as a triumph of science, and it was. But embedded within that triumph was a quiet, rarely acknowledged fact that deserves examination. The system that resolved the crisis, the system of telescopes, algorithms, and human expertise that determined the asteroid would miss Earth, did not detect the asteroid until 2 days after its closest approach. 2024 YR4 passed within 829,000 kilometers of Earth on December 25, 2024. It was discovered on December 27th. For 2 full days, a city-killing asteroid had been closer to Earth than twice the distance to the Moon, and nobody knew it was there. This is not a failure of the system. The asteroid was approaching from a direction and at a brightness level that placed it outside the detection capabilities of the survey telescopes at the time of closest approach. It was found only when it had moved far enough from its closest point to become detectable. But the implication is clear. Had the asteroid been on a collision course during its 2024 approach, rather than its 2032 return, there would have been zero warning. The rock would have arrived, struck Earth, or exploded in the atmosphere, and the first anyone knew about it would have been the flash and the shockwave. Exactly like Chelyabinsk, exactly like Tunguska, exactly like every other impact in human history prior to the invention of asteroid tracking technology. The system works prospectively. It can calculate future encounters and assess risks years in advance. But it does not, and currently cannot, guarantee detection of objects on their current approach. Objects can slip through. Objects can arrive from blind spots. Objects can be too faint, too fast, too small, too close to the sun. The system is a net, and the net has holes. 2024 YR4 slipped through the net on its 2024 passage and was caught only on the outbound leg when it was already moving away. The system then had to race to characterize the object before it faded from view, a race that was won only through the extraordinary deployment of the JWST. The next object might not provide that second chance. The next object might arrive on a direct collision course on its very first approach to Earth, having never been observed before, traveling too fast and from too dark a region of sky for any telescope to catch it. In that scenario, the first indication of the threat would be the impact itself. No Sentry alert, no Torino Scale rating, no IORN notification, just the flash, the shockwave, and the aftermath. This scenario is not theoretical. It is the scenario that occurred at Tunguska. It is the scenario that occurred at Chelyabinsk. And statistical models suggest that it will occur again with an object in the 50 to 100 meter class within the next few hundred to 1,000 years. The probability in any given year is small, but over the span of a century it becomes significant. Over the span of a millennium it approaches certainty. The question that 2024 YR4 ultimately forces us to ask is not Apophis. The answer to that question is complex and contingent and depends on timescales. The question is simpler and more profound. Are we paying attention? Are we investing in the telescopes, the spacecraft, the institutional frameworks, the sustained commitment that the threat requires? Are we treating planetary defense as a permanent necessity or as an occasional curiosity, funded when a scare makes headlines and forgotten when the headlines fade? The story of 2024 YR4 offers reason for both hope and concern. Hope, because the system worked, because humanity detected a threat, mobilized a response, and resolved the uncertainty. Concern, because the system worked only barely, only with the emergency deployment of instruments not designed for the task, and only for an object that happened to be found at a time and in a position that allowed follow-up observation. The margins were thin. The next time, they might be thinner. The universe does not send warnings, it sends rocks, and the interval between the warning and the rock is the only margin we have. 2024 YR4 gave us that margin, and we used it well. The question is what we do with the time between now and the next one, because that time, more than any telescope or spacecraft or algorithm, is the most precious resource in the story of planetary defense. And it is running. Stand back now from the details. Stand back from the orbital calculations and the impact probabilities, from the telescope names and the mission acronyms, from the Torino Scale ratings and the risk corridors. Stand back and look at the whole story. From the moment a Chilean telescope caught a faint smudge of light to the moment the James Webb Space Telescope, 1.5 billion kilometers from Earth, confirmed that neither our planet nor our moon was in danger. Look at the arc of that story and ask what it means. It means, first and most obviously, that the universe is not finished with us. The era of cosmic bombardment, the period during which the inner solar system was pummeled by debris left over from the formation of the planets, is often described as having ended roughly 3.8 billion years ago, during a period called the Late Heavy Bombardment. But that description is misleading. The bombardment did not end, it merely slowed down. The rate of impacts has declined dramatically since the early solar system, but it has never reached zero. Objects continue to strike Earth, at a rate that is low by geological standards, but significant by human ones. The Tunguska class event rate is estimated at once every few hundred to 1,000 years. The Chicxulub class event rate is roughly once every 100 million years. But these are averages, not schedules. The universe does not operate on a timetable. The next 50-meter rock could arrive tomorrow, or it could arrive in 500 years. We do not know. What we do know is that 2024 YR4 represented the single most serious test of humanity's ability to detect and respond to a genuine asteroid threat. And the results of that test are both encouraging and sobering. The encouraging part is real and should not be dismissed. We found the asteroid. We found it roughly 8 years before the potential impact date. We tracked it with a global network of telescopes, coordinated by international institutions, using protocols that had been developed specifically for this purpose. We deployed the most powerful space telescope in existence to gather data that ground-based instruments could not provide. We communicated the risk to the public with a degree of transparency and honesty that, while imperfect, was vastly better than the alternative of secrecy or denial. And we resolved the threat definitively within 14 months of the initial discovery. Every one of these steps represents a triumph of human foresight, cooperation, and scientific capability. The sobering part is equally real and equally important. The asteroid was found by accident by a survey telescope that happened to be looking in the right direction on the right night. It was found only after its closest approach, when it was already moving away from Earth. The orbit was uncertain for weeks, during which the probability of impact rose to an all-time record. The resolution of the orbit depended critically on the JWST, a one-of-a-kind instrument that was not designed for this purpose and cannot be relied upon for future crises. The observation gap, the period during which the asteroid was invisible to ground-based telescopes, nearly left the world in years-long uncertainty, and the fundamental detection gap, the inability to see objects approaching from the direction of the Sun, remains unaddressed. If 2024 YR4 had been on a collision course, the system might have provided enough warning for deflection, but only if the deflection mission could be designed, built, and launched within roughly 7 years. A timeline that has never been achieved for any planetary defense mission. If the orbit had not been resolved until the asteroid reappeared in 2028, the remaining lead time of 4 years would almost certainly have been insufficient for deflection. In that scenario, the response would have been limited to civil defense, calculating the impact point, evacuating the area, and hoping the evacuation was complete before the rock arrived. For a 50-kilometer radius blast zone in a corridor that crosses some of the most densely populated cities on Earth, evacuation would be a logistical nightmare of unprecedented proportions. Moving millions of people out of a potential impact zone in the months or years before an uncertain impact date would require international coordination on a scale never attempted, and the uncertainty itself would be the hardest part. How do you evacuate a city based on a probability? How do you tell people they might need to leave their homes, their jobs, their lives, based on a number that might drop to 0 next week, or might rise to certainty? These are not hypothetical questions. They are the operational questions that the next asteroid threat will force the world to answer, and the answers need to be worked out in advance, not improvised in the heat of crisis. The implications of the 2024 YR4 episode extend beyond planetary defense into the broader question of how civilization manages long-term, low-probability, high-consequence risks. Climate change, pandemic preparedness, nuclear weapons, asteroid impacts. These are all threats that operate on timescales longer than political cycles, that require sustained investment in prevention rather than reaction, and that punish complacency with catastrophe. The pattern is familiar. A scare captures public attention, funding increases briefly, then the scare fades, attention shifts, and the underlying vulnerability remains. The story of 2024 YR4 will, in time, fade from public memory. The asteroid's name will be forgotten by most people who once followed the news. The 14-month drama of escalating probabilities and emergency telescope deployments will blur into the general background of things that happened. But the asteroid will not forget. It will return, not this time as a threat, but as a reminder. A 60-meter reminder, tumbling through space on its 4-year orbit, that the solar system is not a museum. It is an active, dynamic, hazardous environment, and the only barrier between its hazards and our survival is our own vigilance. The question is whether that vigilance will be sustained, whether the investments in planetary defense that the 2024 YR4 crisis highlighted will be made and maintained, whether the NEO Surveyor will launch, and the next generation of survey telescopes will be built, and the international frameworks for response will be strengthened, or whether the usual pattern will reassert itself: scare, brief attention, gradual neglect, and a slow return to the comfortable assumption that the sky is empty and the future is safe. History suggests the latter. Human beings are not, as a species, well equipped for sustained vigilance against threats that are real but remote. We are built for immediate dangers, for the predator in the grass, for the storm on the horizon. We are not built for dangers that may arrive in decades or centuries, that exist as probabilities rather than certainties, and that require action now to prevent consequences that will be borne by people who have not yet been born. But the capacity to overcome our limitations is also part of what makes us human. We built the pyramids and the cathedrals, projects that spanned generations. We eradicated smallpox, a campaign that required decades of global coordination. We put human beings on the moon, an achievement that seemed impossible until it was done. The question is not whether we are capable of sustained vigilance against the asteroid threat. We clearly are. The question is whether we choose to exercise that capability. 2024 YR4 made the choice clear. The cost of vigilance is modest. A few telescopes, a few spacecraft, a few hundred scientists and engineers dedicated to watching the sky. The cost of failure is measured in cities. This is where the story ends. Not with a collision, not with a near miss, not even with a dramatic rescue. It ends with a quiet resolution, a number dropping to zero, a rock continuing on its orbit, a world turning its attention to other things, the stars unchanged, the sky indifferent. The night, as always, full of light too old and too distant to care about the small, warm, fragile world that orbits a modest star in an ordinary arm of an unremarkable galaxy. 2024 YR4 will pass close to the Moon on December 22, 2032. It will come within roughly 21,000 kilometers of the lunar surface, close enough to be a spectacular target for telescopes, far enough to cause no harm. It will then continue on its orbit, swinging back out toward the outer reaches of the inner solar system, fading from view, and returning, as it has returned for billions of years, on its 4-year cycle. It is a 60-meter rock, a grain of sand in the cosmic scale, the kind of object that exists in the hundreds of thousands throughout the near-Earth population, most of them unseen, most of them untracked, each one carrying enough kinetic energy to reshape the landscape of a small country. For a few weeks in early 2025, this particular grain of sand was the most closely watched object in the solar system. Hundreds of astronomers trained their instruments on it. The most powerful space telescope ever built was diverted to observe it. Governments were notified. Risk corridors were published. More than 100 million people lived within the potential impact zone. The probability of impact, 1 in 32, was the highest ever recorded for any large asteroid in the history of modern tracking. And then the orbit was resolved, the probability dropped, and the world moved on. But the world should not move on entirely, because the lesson of 2024 YR4 is not that we were lucky. The lesson is that luck is not a strategy. The question posed by the title of this documentary, whether 2024 YR4 was the highest risk asteroid in NASA history, has a clear and definitive answer. Yes, it was. On February 18, 2025, with a 3.1% probability of impacting Earth, it surpassed the previous record held by Apophis and became the most threatening asteroid ever documented by modern planetary defense systems. That record may stand for years or decades, or it may be broken tomorrow, because the population of near-Earth objects is vast, largely uncatalogued, and constantly refreshed by the gravitational dynamics of the solar system. The next record holder is already out there, orbiting in the darkness, waiting to be found. The real question is not whether 2024 YR4 was the highest risk. The real question is what we do with the knowledge it brought us. We know now that the system works. We know that it has gaps. We know that detection depends on a patchwork of ground-based telescopes, supplemented in emergencies by a space telescope that was built for an entirely different purpose. We know that deflection is possible, but requires years of lead time that may not always be available. We know that communication with the public is challenging and imperfect, but better than the alternative of silence. And we know that the threat is permanent, a feature of the solar system that will persist for as long as the sun burns and the planets orbit. If the 4.6 billion year history of the solar system were compressed into a single calendar year, all of recorded human history would fit into the final second before midnight on December 31st. The era of planetary defense would occupy less than a millisecond. We are new to this, we are young, we are learning, and the curriculum is unforgiving, but we are also remarkable. In less than 30 years, we built a global detection network, catalogued tens of thousands of near-Earth objects, proved that asteroid deflection is physically possible, created international institutions to coordinate our response, and handled the highest-risk asteroid in history without panic, without chaos, and without catastrophe. We did all of this with modest budgets, small teams, and instruments that are already being superseded by better ones. The trajectory of capability is upward. The question is whether it is upward fast enough. Imagine the sun were a basketball sitting in the center of a football field. The Earth would be a pea 26 meters away. The moon would be a pinhead. about 6 centimeters from the P, and 2024 YR4, the rock that terrified the world, would be a particle of dust, invisible to the naked eye, drifting through the space between the P and the edge of the field. That particle of dust was, for a few extraordinary weeks, the most dangerous object in the known universe, because it happened to be aimed roughly in the direction of the P, and the people living on the P, who had only recently learned to look up and notice the dust, managed to determine that it would miss, by a margin so thin that it required the most powerful telescope in existence to measure it. That is the story. That is what happened. A grain of dust, a fragile world, and the narrow margin between safety and catastrophe. The night sky is beautiful tonight. It always is. The stars burn with the same ancient light they have burned with for billions of years. The moon hangs in its orbit, serene and unmarked, its surface still bearing the scars of impacts that occurred before any human being drew breath. And somewhere out there, beyond the reach of our best telescopes, below the threshold of our most sensitive detectors, a rock is moving. It has been moving for longer than the Earth has existed. It does not know about us. It does not care. But we know about it. Or rather, we know that it exists, even if we do not yet know its name. And that knowledge, the knowledge that the threat is real, that it is permanent, and that we possess, for the first time in the history of life on this planet, the ability to do something about it, that knowledge is the most important thing 2024 YR4 leaves behind. The sky is not empty. It was never empty. And watching it is not a luxury. It is a necessity, as fundamental as any we possess. The silence of the night sky is not peace. It is patience. And patience in the cosmos always ends the same way, with a rock.